Welcome to today's problem walkthrough. In this session, we'll be tackling problem number 30, substring with concatenation of all words. This problem challenges us to find all starting indices of substrings in a given string that are formed by concatenating all words from a given list exactly once and without any intervening characters. Let's dive in and explore the solution step by step. In this problem, we're working with a string S and an array of strings called words. Each string in the words array has the same length. The goal is to find all starting indices in S where a concatenated substring can be formed using all the strings in words exactly once, in any order, and without any gaps or additional characters. Essentially, we need to identify every position in S that starts a valid concatenated substring. The output will be a list of integers representing these indices. The constraints ensure that the input sizes are manageable, with S having a maximum length of 10,000 characters and words containing up to 5,000 strings, each up to 30 characters long. Let's explore some examples to clarify this further. For the first example, the input string S is bar foo the foo barman, and the words array contains foo, bar. A valid concatenated substring must include both foo and bar exactly once, in any order. In this case, we find two such substrings, bar foo, starting at index 0, and foo bar, starting at index 9. Both substrings meet the problem's requirements, so the output is 0, 9. This demonstrates how we identify and record the starting indices of valid concatenated substrings. Now, in the second example, the string S is word good best word, and the words array contains word, good, best, word. Here, the requirement of using all words from the array exactly once cannot be met. The word appears twice in the words array, but no substring in S includes it twice while also incorporating the other words. As a result, there are no valid concatenated substrings, and the output is an empty list. In the third example, the string S is bar foo foo bar the foo barman, and the words array contains bar, foo, the. This time, we find three valid substrings that use all the words exactly once. These are foo bar, starting at index 6, barth, starting at index 9, and the foo, starting at index 12. Each of these substrings is formed by concatenating all the words in any order, without gaps or extra characters. The result is a list of starting indices, 6, 9, 12. When solving this problem, it's important to consider edge cases. For example, if words contains duplicate words, the solution must account for the correct frequency of each word in the concatenation. Similarly, if words contains only a single word, the solution must handle this case correctly. Additionally, if S does not contain any of the words in words, the output should be an empty list. These scenarios highlight the importance of carefully managing the constraints and ensuring the solution works for all valid inputs. To start, let's discuss the brute force approach. The idea here is straightforward. We iterate through all possible substrings of the string S and check if each one forms a valid concatenation of all words provided in words. This involves two critical steps. First, we ensure the substring's length matches the total length of all concatenated words, which is calculated as len, words, asterisk len, words, 0. Then, we split the substring into equal parts, each of length len, words, 0, and verify whether all words appear with the correct frequency using a frequency map. While this is intuitive, the computational cost is high. Generating all substrings takes O, and superscript 2, and verifying each substring adds an additional O, k, where k is the number of words. This results in a time complexity of O, and superscript 2 asterisk k, which can quickly become infeasible for large inputs. This inefficiency is the main downside of the brute force method, making it unsuitable for real-world scenarios where performance is critical. Now, to overcome the inefficiencies of the brute force method, we can use the optimized sliding window approach. This method eliminates redundant computations by leveraging a fixed window size and word frequency maps. The first observation here is that any valid substring must have a fixed length, which we calculate as window_length equals len, words, asterisk len, words, 0. Instead of repeatedly splitting and rechecking substrings, we use a sliding window over S and dynamically adjust the frequency counts of words within the window. If the frequency of words in the current window matches the target frequency map, we record the starting index of the window. The algorithm begins by precomputing the frequency map for the words array. Then, we iterate through the string S using multiple starting points, from 0 to len, words, 0, 1, to handle overlapping windows. For each starting point, we slide a window of size window_length and adjust word counts as the window moves. This drastically reduces redundant checks and improves efficiency. The complexity of this approach is significantly better. Building the frequency map is O, K, and sliding the window is O, N. When accounting for multiple starting points, the total complexity becomes O, N asterisk K, making this approach much faster and more scalable than brute force. The sliding window approach is the chosen strategy for this problem because it strikes an excellent balance between efficiency and simplicity. The pivotal realization here was that by dividing the problem into overlapping fixed-size windows, we could avoid redundant checks and achieve linear scalability relative to the size of the input string. This makes the method highly practical for handling large inputs. Comparing trade-offs, the brute force approach, while simple to implement, is computationally expensive and impractical for larger datasets. The sliding window approach, on the other hand, requires some initial setup like frequency maps, but it is far more efficient and scalable. Alternatives like hashing or dynamic programming might seem appealing but often introduce unnecessary complexity without significantly improving the runtime beyond what the sliding window approach achieves. Therefore, for this problem, the sliding window method offers the best balance of simplicity, performance, and scalability, making it the ideal solution to use in real-world applications. The problem we're solving is to find all starting indices of substrings in a string S that are a concatenation of all the words in the array words, appearing exactly once and without any spaces or additional characters in between. Importantly, each word in words has the same length. To tackle this, the first step is to understand a key constraint. The total length of any valid substring must be equal to L, which is calculated as the number of words in words multiplied by the length of each word. For example, if words contains 2 words of length 3, the total length of the concatenated substring will be 6. Another critical point is that the words can appear in any order, but they must all be present exactly once. Next, we precompute the frequency of each word in the array words using a dictionary called word_count. This frequency map will allow us to efficiently validate if a substring contains the correct number of each word as we iterate through the string S. The precomputed word_count map is essential for quickly checking if a substring contains valid word frequencies. To efficiently search for valid substrings in S, we use the sliding window technique. Here's how it works. We iterate through the string S using a sliding window of size L, which is the total concatenated length of the words. For every starting index I, we extract the substring S, I plus L, and divide it into chunks of length equal to each word. Using a temporary dictionary scene, we count the frequency of these chunks and compare it with word_count. If the two maps match, we know this starting index forms a valid substring. To implement this, we initialize key variables, n as the length of S, word_len as the length of each word, number_words as the number of words in words, and L as the total concatenated length. Additionally, we check an edge case. If the string S is shorter than L, no valid substring can exist, so we immediately return an empty list. Finally, we loop over possible starting indices, and for each, we maintain a sliding window using left and right pointers. The right pointer expands the window to include chunks of size word_len, while the left pointer adjusts to maintain a valid window. As we process each chunk of the substring inside the window, we first check if the chunk is a valid word in word_count. If it is, we increment its count in the scene map. However, if the count of this word exceeds its expected frequency in word_count, we adjust the window by moving the left pointer forward and decrementing the counts of the words that are sliding out of the window. This ensures the window remains valid. If the window size equals L and the word counts in scene and word_count match, we've found a valid starting index, so we add the left pointer to our result list. On the other hand, if the chunk is not a valid word, we reset the scene map and move the left pointer to match the right pointer, effectively starting a new window. Once all possible starting indices have been processed, we return the list of valid starting indices and result. The sliding window technique is highly efficient because it avoids recomputing word frequencies for every possible substring. Instead, we make incremental adjustments to the window by adding and removing words as needed. This optimization significantly reduces the time complexity compared to a brute force approach. Precomputing the word _count map is another key efficiency gain, as it allows constant time lookups to validate words. By splitting substrings into fixed-size chunks equal to the word length, we ensure alignment with word boundaries. Additionally, the algorithm handles edge cases gracefully. If the string S is shorter than L, we immediately return an empty result, avoiding unnecessary computations. The approach also accounts for duplicate words and words by maintaining accurate frequencies in word _count. These considerations make the algorithm robust and scalable for larger inputs. Let's analyze the complexity of the algorithm. For time complexity, the outer loop iterates word _len times to handle different offsets for the sliding window. Within each offset, the inner loop processes approximately n/word _len windows, and each window involves operations on number _words chunks. This gives us a total time complexity of O, n * number _words. For space complexity, the word _count and scene hash maps each store up to number _words entries, resulting in a space complexity of O, number _words. Both the time and space complexities are efficient, making this approach practical for solving the problem within constraints. To solidify our understanding, let's walk through an example. Given the string S equals bar foo the foobarman and the array words equals foo, bar, we first precompute the word _count map as foo, 1, bar, 1. Using a sliding window, we start with the first window at index 0, extracting the substring S, 0:6, equals bar foo. Splitting this into chunks of size 3 gives us bar, foo. The frequency of these chunks matches word _count, so we add index 0 to our result. We repeat this process for all possible starting indices, and the output is 0, 9, representing the starting indices of valid substrings in S. Here, we define the find substring function inside the solution class. The function takes two inputs, the string S and a list of words. The goal is to find all starting indices of substrings in S that are a concatenation of every word in words exactly once and without any intervening characters. First, we handle edge cases by checking if either S or words is empty. If so, we return an empty list. Next, we calculate some key values, word _len, which is the length of each word since all words are the same size, number _words, which is the total number of words in the list, and substring _len, which is the total length of a valid substring that includes all the words concatenated. We also initialize a dictionary called word _count to keep track of how many times each word appears in the list of words. After this setup, we proceed to iterate through the string in chunks based on the word length, so we establish a loop starting at each index up to word _len. Within this loop, we use two pointers, left and right, to define the window we're currently examining. We also initialize current _count to track word frequencies within the current window and a variable count to measure how many valid words we've seen. The main logic begins with a while loop, where we extract substrings of length word _len from S starting at right. Each substring is stored in the variable word, and the right pointer moves forward by word _len. If the extracted word exists in our word _count dictionary, we increment its count in current _count and update our count variable to reflect the number of valid words we've encountered so far. At this stage, if the count of the current word in the current _count dictionary exceeds its expected count in word _count, it means our window contains too many occurrences of that word. To fix this, we shrink the window by repeatedly moving the left pointer forward by word _len. During this process, we adjust the count of the word being removed from the window and decrement the overall count of valid words. Now, if the count matches number _words, it indicates that the current window contains all the words from the list exactly as required. We then append the left pointer's value to the result list, which stores all valid starting indices. On the other hand, if the extracted word is not in word_count, it means the current window is invalid. In this case, we reset the current_count dictionary, set count to 0, and move the left pointer to the right pointer's position, effectively starting a new window. Once all iterations and checks are complete, the function returns the result list, which contains all indices where valid substrings were found. Here, we are implementing a solution to find all starting indices of substrings in a given string S that are a concatenation of all words in the array words. To begin, we check for edge cases where the input string or words array is null or empty, immediately returning an empty list if that's true. Next, we calculate some important variables, word length, which is the length of each word in the array, number words, the total number of words, and substring length, which represents the total length of the concatenated substring we are looking for. We then create a word count map to store the frequency of each word in the words array. This map helps us track how many times each word is expected to appear in a valid substring. After initializing an empty list result to store the starting indices of valid substrings, we begin iterating through the string with a loop that starts at different offsets, ranging from 0 to word length 1. This allows us to evaluate all possible alignments of words within the string. For each offset, we initialize 2 pointers, left and right, both starting at the offset position, and a current count map to track the frequency of words encountered within the current window. We also use a count variable to keep track of how many valid words have been matched so far. The inner while loop ensures that we only process substrings that are within bounds, extracting words of word length from the string, starting at the right pointer. Once the word is extracted, we move the right pointer forward by word length. If the extracted word exists in the word count map, we increment its count in the current count map and increase the count variable. If the frequency of the word in current count exceeds the allowed frequency in word count, we adjust the window by moving the left pointer forward in increments of word length, reducing the count of words being removed from the window and updating the count accordingly. When the count matches the total number of words, it means the current window contains a valid substring, so we add the left pointer to the result list. On the other hand, if the extracted word is not in word count, we reset the current count map, set count to 0, and move the left pointer to the right pointer. This ensures that we skip over invalid regions of the string. After iterating through all possible offsets and processing the string, the method returns the result list containing all valid starting indices. This approach ensures that we efficiently check all possible substrings while maintaining a balance between complexity and performance, leveraging the sliding window technique and hash maps for optimized word counting. To solve this problem, let's start by analyzing example 1, where the string S is bar foo the foobarman and the list of words is foo bar. First, we initialize some key variables. The length of each word, word_len, is 3 since all words in the list are of equal length. The total number of words, number_words, is 2, and the length of the concatenated substring we're searching for, substring_len, is 6, which is word_len multiplied by number_words. We also create a frequency map, word_count, to record the occurrence of each word in the list. Here, foo and bar each appear once, so word_count is foo 1 bar 1. Next, we iterate through the string using a sliding window approach. The outer loop runs from I equals 0 to word_len 1 to account for all possible starting positions within the word length. In the subiteration where I equals 0, we initialize our sliding window pointers, left and right, both set to 0. We also define current_count to track the frequency of words in the current window and a count variable to track the number of valid words matched so far. As we move the right pointer, we extract substrings of length word_len. For instance, at right equals 3, we extract bar, which exists in word_count. We update current_count to bar 1 and increment count to 1. Similarly, at right equals 6, we extract foo, again finding a match. Now, current_count becomes bar 1 foo 1 and count reaches 2, which equals number_words. This indicates we've found a valid substring starting at left equals 0, so we add 0 to our result. After this, we reset current underscore count and count as we move beyond the substring length. For I equals 1 and I equals 2, the logic remains the same, but no valid substrings are found in those subiterations. The final result for example 1 is 0, 9, as we found valid substrings starting at indices 0 and 9. Now, let's move on to example 2, where the string S is word good best word and the list of words is word good best word. To begin, we initialize the same variables as before. Here, word underscore len is 4 because the words have a length of 4. The total number of words, number underscore words, is 4, and the target substring length, substring underscore len, is 16. The frequency map, word underscore count, becomes word 2, good, 1, best, 1, as word appears twice. Again, the sliding window approach iterates through the string. For I equals 0, we initialize left, right, current underscore count, and count as before. As the right pointer moves, we sequentially extract words like word, good, and best. However, the second occurrence of good exceeds its allowed frequency in word underscore count, so we adjust the left pointer to shrink the window and restore validity. Despite this adjustment, we don't find any valid substrings of length 16 for this iteration. Similarly, for I equals 1, I equals 2, and I equals 3, no valid substrings are found because the sliding window either exceeds word frequencies or fails to match all words in the list. The final output for example 2 is an empty list, as no valid substrings were found. Let's examine example 3, where the string S is ling mein drabo foing ding bear wing mon ki pound cake and the list of words is foo, bar, wing, ding. Here, the words are all of length 4, so word underscore len is 4, number underscore words is 4, and substring underscore len is 16. The frequency map, word underscore count, becomes foo, 1, bar, 1, wing, 1, ding, 1. Using the same sliding window approach, we iterate over the string. For I equals 0, as the right pointer moves, we extract substrings like ling, mind, and so on, until we find a valid substring starting at index 13, where the words foo, bar, wing, and ding match exactly with the required frequencies. At this point, we add 13 to our result. For I equals 1, I equals 2, and I equals 3, the sliding window detects mismatches or invalid substrings, resetting current underscore count as needed. No additional valid substrings are found in these subiterations. The result for example 3 is 13. Now, let's highlight some key insights from the solution. The sliding window technique allows us to efficiently search for valid substrings without repeatedly recalculating word frequencies. The word underscore count dictionary helps track the target frequencies of the words, while current underscore count keeps track of the words in the current window. When a word exceeds its allowed frequency, we adjust the left pointer to shrink the window, ensuring that the substring remains valid. This optimization is crucial for handling large inputs. The overall time complexity of the solution is n asterisk word underscore len, where n is the length of the string. This efficiency comes from iterating through the string only a limited number of times based on the word length, making the approach scalable for larger inputs. Here, we analyze the time complexity of the solution by breaking it into its components. First, the outer loop iterates over word underscore len, which is the length of each word. This loop runs word underscore len times, but since word underscore len is constant for all words and typically small compared to the size of the string S, its contribution is considered 1. Next, we examine the sliding window loop. For each starting position, the right pointer traverses the string S in increments of word underscore len. In the worst case, it processes the entire string of length n, contributing n/word underscore len iterations per starting position. Since there are word underscore len starting positions, this simplifies to n. So, the traversal of the sliding window dominates the time complexity at this point. Now, focusing on the inner while loop, the operations include slicing substrings and updating the current underscore count dictionary. These operations are performed in constant time for each word, contributing 1 per iteration. Additionally, the while current underscore count, word underscore count, word condition adjusts the left pointer. In the worst-case scenario, the left pointer moves across the entire string S once, which adds another O, N, to the total complexity. Combining all components, the overall time complexity is O, N, where N is the length of the input string. For space complexity, we start with the word_count dictionary, which tracks the frequency of each word from the words list. Since there are number_words unique words, this dictionary requires O, number_words, space. Similarly, the current_count dictionary, which temporarily holds frequencies within the sliding window, also requires O, number_words, space. Both dictionaries depend on the number of unique words, not the string size. We also account for the space required by the result list, which stores valid starting indices. In the worst case, if every possible substring of length substring_len is valid, this list may hold up to O, n/word_len indices equivalent to O, n. While the total space complexity is O, number_words plus n, the term O, n, dominates because number_words is usually much smaller than the size of the string. Comparing this to a brute force approach, the optimized solution is far more efficient. A naive method would generate all possible substrings and check each one against permutations of words, leading to O, n asterisk number_words, time complexity, which is impractical for large inputs. In contrast, the sliding window and hash map technique reduce unnecessary checks, achieving an optimized complexity of O, n. To better understand performance, we analyzed best, average, and worst cases. In the best case, if all words in the words list are identical, such as the current_count dictionary updates are minimal, and the solution runs efficiently in O, n. For average cases, typical inputs with multiple distinct words still maintain O, n complexity, although the constants involved may be slightly larger due to frequent updates to the current_count dictionary. The worst case arises when the string S contains many overlapping substrings that partially match words, requiring frequent adjustments of the left pointer. Even then, the complexity remains O, n. Mathematically, the sliding window processes each character in S at most twice, once as the right pointer moves forward and potentially again when the left pointer adjusts. This ensures the total operations are proportional to the length of S, confirming the time complexity is O, n. When solving this problem, there are a few common mistakes to watch out for. One major mistake is ignoring edge cases like empty strings, empty word lists, or when all the words are identical. For example, if the string S is an empty string or the words list is empty, the expected result should typically be an empty list. Failing to handle this can lead to runtime errors, which is why testing these scenarios is so critical. Another common issue is mismanaging word frequencies. Some solutions incorrectly assume that all words in the list are unique, but if the words can repeat, you need to ensure that the correct frequency of each word is checked. A good approach here is to use a dictionary or hash map to store the word frequencies and compare to the frequency of words in the current substring. Finally, incorrect updates in the sliding window approach can cause inefficiencies or errors. For instance, when you encounter a word not in the words list, you need to move the window to the start of the next possible substring. Failing to do this can result in unnecessary processing or invalid results. Another issue to be mindful of is inefficient substring checks. A naive approach that generates all possible substrings results in a time complexity of O, n cubed, which is far too slow for large inputs and will likely fail under time constraints. Instead, you can optimize using sliding windows or hash maps to reduce the complexity to O, n. Additionally, it's important to account for the length constraint of the concatenated substring. If the total length of words multiplied by the length of one word doesn't match the length of the current substring, you can immediately skip it. This small optimization can save significant processing time. From an interview perspective, this problem tests your ability to combine techniques like sliding windows and hash maps, so being able to recognize and implement these patterns efficiently is key. While explaining your solution, it's a good idea to start with a brute force approach but quickly pivot to optimizations. Demonstrating awareness of time complexity trade-offs will impress interviewers. Also, don't forget to discuss edge cases proactively, as this shows thoroughness and attention to detail. Finally, think about generalizations of the problem, such as handling words of different lengths or inputs with special characters, as these are common follow-up questions in interviews. This problem shares similarities with a few other problems that you might want to explore to deepen your understanding. For instance, LeetCode Problem 3, Longest Substring Without Repeating Characters, focuses on applying the sliding window technique to substring problems. LeetCode 76, Minimum Window Substring, is another great example that uses sliding windows combined with frequency matching, which is very relevant here. Similarly, LeetCode 438, Find All Anagrams in a String, relies on hash maps to track frequencies, making it a valuable practice problem. Lastly, LeetCode 560, Subarray Sum equals k, is another problem that emphasizes efficiently finding subarrays with specific properties, which is conceptually similar to substring problems. Working through these related problems will help reinforce your skills with techniques like sliding windows, hash maps, and pattern recognition. There are alternative approaches to solving this problem, each with its own trade-offs. The brute force approach involves generating all substrings of the appropriate length and checking if they are a valid concatenation of the given words. While this method is simple to implement, it has a time complexity of n cubed, making it highly inefficient for large inputs. A more optimal approach is the sliding window technique combined with hash maps. Here, you use a fixed-size sliding window to validate substrings by tracking word frequencies in a hash map. This approach is more complex to implement but has a significantly improved time complexity of n*m, where m is the number of words. Another alternative is sorting-based validation, where you sort the words list and compare it to the sorted list of words in each substring. While easier to implement than hash maps, this method is slower, with a complexity of n*m*log m due to the sorting step. Each approach has its strengths, but for interviews or competitive programming, mastering the sliding window with hash maps is the most practical and efficient solution. Great job making it through this problem. To recap, we used a combination of sliding windows and hash maps to efficiently solve the substring with concatenation of all words. Remember to practice variations of this problem to strengthen your understanding of these techniques. Thanks for watching, and don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!